Alright, so in this video we covered the introduction to the Laplace transform, where we will define the Laplace transform and find the Laplace transform of elementary function. Alright, well, before getting to what the Laplace transform is, let's define in general what an integral transform is. So in general, we want to obtain a new function called f of, in general we call it f of u, so that variable, it's a variable in a new domain with a new variable, and this is given by some integral of some function of two variables. Let's call it x and u, and some function of x that we want to transform. For the limits of integration, well, depending on the kind of transformation that we want to do, well, but in general, we want to evaluate or find the integral transform of a function whose domain goes between 0 and infinity. Now, f of x right here is the function to be transformed, right? And this function k of x u, this is called the kernel of the transformation. Or the transformation, yes. All right. Well, what is that kernel of the transformation? So, well, in an integral transform, the kernel of the kernel, also called the nucleus or the integral kernel, it's a function of two variables, which is denoted with a k of x and u, or t and s, depending on the variables we use, and that defines the specific transformation being performed. So this function in reality essentially specifies how the input function is integrated to produce the transform function. All right, so what do we do in this case? So an integral transform takes some function f of x and transforms it into some function f of u, or whatever other variable that we specify through this integral operation. All right, so now what is this kernel of this transformation? Well, so the kernel function acts like a weight or a factor that modifies the original function f of x before it gets integrated to produce the new transform function. Actually, we will define many different kernel functions that will define many different transforms, each of them serving a specific purpose in transforming functions between other different domains. All right, so and in particular, well, in essence rather, this kernel defines the nature of the transformation by specifying how the input function is weighted and integrated to produce the output function. Well, so now let's define the Laplace transform, what's going to do. Okay, so the Laplace transform will transform some function f of t into a new function that we're going to call f of s, big F of s. That's the related f of u in general, but in this case, for the Laplace transform, we will obtain a function of s. Well, what is the Laplace transform? Well, so let f be a function defined for all positive values, including 0. Then the integral from 0 to infinity of e to the negative st, times f of t dt, will produce this new function, which is the Laplace transform. All right, so we have a special symbol for the Laplace transform. It's like a very fancy looking L. Okay, and well, the kernel of the transformation for the Laplace transform is e to the negative st. Well, there's other transforms that well, maybe not in this class, but in other engineering courses and mathematics courses, such as the Fourier transform or the Z transform in engineering. Well, those transforms have their own kernels, or the kernel functions, that will transform functions into new transformed functions. All right, now a little bit of notation. For instance, if we want to find the transform of f of t, we would get f of s, big F of s. If we find the Laplace transform of g of t, then we obtain uppercase g of s. The Laplace transform of lowercase y would be uppercase y of s. All right. So um, this is just a matter of notation. All right. So, okay, how do we find the Laplace transform? Well, first we're going to do a couple evaluating the integral, and then we're going to discuss a few formulas to get the Laplace transforms of those elementary functions. Think of like when you first learn about finding derivatives, you learn a long process that is called the limit process to get the derivative of a function. Well, we will talk about a somewhat long process, to find the Laplace transform, although we're going to abbreviate a lot of the work to do this quicker. Okay, so let's get and find the Laplace transform of an integer or any number, not just an integer, any number. But I chose the number 4 to find its Laplace transform. Well, in this case, the function to be transformed is f of t equals to 4, which, using the definition of the Laplace transform, so that'll be the integral from 0 to infinity of e to the negative st times 4 dt. Okay, this 4, it's just a multiple constant here. All right, well, so I'm going to take that 4 outside of the integral from 0 to infinity of e to the negative st dt. Okay, well, so look at this integral. Looks fairly simple to evaluate. However, we would need to go through the process of rewriting this integral as an improper integral because as in terms of a limit problem, because that's how we treat type 1 improper integrals. Okay, however, that may be a little tedious, so lucky for us, we have already gone through a lot in our notes on the gamma function that we discussed before getting into the Laplace transform. Well, but wait a minute, how can that integral be written in terms of the gamma function? Well, so the gamma function, let me rewrite it at the top, okay? So the gamma function, which is the integral from x, or the integral from 0 to infinity of x to the n e to the negative ax dx equals either gamma of n plus 1 over a to the n plus 1, which is the same as saying n factorial over a to the n plus 1. All right, well, how can we write this integral in terms of the gamma function? Well, so hopefully we agree. Well, this is 4 times the integral from 0 to infinity of, how about this is t to the 0 power e to the negative st dt. Well, in this case, well, let's recall how we evaluated integrals using the gamma function. So n equals to 0 and a equals the number that multiplies the variable t in the exponential, which in this case is the letter s, without the negative exponent. All right, so how do we do this? Well, don't forget about the 4. So this is equal to 4 times 0 factorial over s to the 0 plus 1 by the definition of the gamma function. That is, okay, so 0 factorial, which is 1, 1 times 4, that equals to 4, 0 plus 1 equals to 1. So 4 over s is the Laplace transform of the function f of t equals to 4. That means the Laplace transform of 5 would be 5 over s. The Laplace transform of 1 would be the number, which is 1 over s. The Laplace transform of any number, can be an integer, a rational, an irrational, etc., is 4 over s. All right. Okay. What about the Laplace transform of t? So number 1, the function to be transformed would be f of t equals to what is that? T. All right. So this would be the integral from 0 to infinity of e to the negative st times t. Okay, but actually I'm going to write the t in the front, e to the negative st, dt. And guys, well, if we were to evaluate this integral using, by the methods of integration that we know from calculus 2, that is using integration by parts, that's going to take forever. And guys, well, and again, every single differential equations textbook usually goes through the process of integration. However, in my class, I'm taking a different approach. That's why we spend a couple lectures discussing the gamma functions, because many of these integrals in the Laplace transform look exactly like those integrals we evaluated using the gamma function, which is way quicker to evaluate rather than going through the process of integration by parts. All right, that being said, well, so here we have n equals to 1 and a again equals to s. All right, a, it will always be s. All right, because that's the number. Yes, technically it's a letter, a variable, but yes, we will take that as a constant. That is s. A equals to s. All right, so this will be number 1, 3 factorial divided by the quantity is a, which is s, to the no, that's actually 1 factorial, not 3 factorial. I was looking at the other example. And over s to the 1 plus 1. And 1 factorial equals to, okay, let me make it look like 1 factorial. There you go. That's 1 over s squared. Quicker rather than going through the process of integration by parts, all right? Especially because letter C, the Laplace transform of t cubed, where the function to be transformed will be t cubed, all right? So evaluating the Laplace transform of t cubed would be the integral from 0 to infinity of t cubed e to the negative st dt. Well, in this case, again, okay, let's list n equals to 3 and a equals to s. Okay, evaluating the Laplace transform rather using the gamma function here, that is n factorial, which is 3 factorial, over s, which is a, raised to the 3 plus 1, which is 3 factorial equals to 6, and s to the 3 plus 1 equals to s to the 4th power. And that is the Laplace transform using the integral, but rather than evaluating the integral using integration by parts, which, by the way, would be madness, because look at this. It would require an integration by parts process 3 times, and well, that's kind of long. Again, the gamma function is our best friend here. All right, well, let's change the type of function that we will find the Laplace transform of. All right, so for the next one, let's find the Laplace transform of e to the 5t. So f of t equals to e to the 5t. All right, so that is the integral from 0 to infinity of the function to be transformed e to the 5t e to the negative st. Okay, let's not confuse the s with the 5. So hopefully I can do the number and the letter differently. Okay, so let's play with the exponentials here, and okay, use lots of exponentials to write everything in terms of one single exponent or one single exponential. So that is the integral from 0 to infinity of e to the 5t minus st dt. Well, let's do some factoring, but actually, guys, I'm going to factor the negative and the t. So I'm going to factor, okay, that's the integral from 0 to infinity e to the negative sign, that is 5 minus, or rather s minus 5 instead, s minus 5, because if we factor the negative, the s becomes positive, that goes first, and then the 5 becomes negative, and that times t. All right, and dt. Okay, so here we will evaluate the integral of an exponential function. That is, we're using a different color. Let me show you how we evaluate this integral. So that's the integral of e to the a t dt. That is 1 over a e to the a t plus c. All right. Well, I mean, in this case, we're going to have limits of integration. So this will be, the integral will be equal to, okay, let me use some color. Okay, so that equals, so this is negative constant, negative 1 over s minus 5 e to the negative s minus 5 t evaluated between 0 and infinity. All right, well, so because this integral is improper, we need to use limit notation in order to evaluate the integral for the upper limit. Well, so number one, this will be negative 1 over s minus 5. Okay, I'm going to open curly braces here. I'm going to write this as a limit as b approaches infinity of e to the negative s minus 5 t, or rather b, call it b rather. All right, so this is only for the upper limit, but for the lower limit we can directly substitute and evaluate at 0. That is e to the negative s minus 5 times 0. Okay, and close the curly braces. Well, let's talk about this expression, these results. Okay, so number one, e to the 0, that's really equal to 1. However, where is this limit going to go to? So for b approaching infinity, okay, but actually this would make e to the negative infinity. But what is e to the negative infinity? That equals to 0. So this will be, okay, let's keep writing our results. This equals to, so negative 1 over s minus 5 times 0 minus 1. Okay, 0 minus 1 is negative 1 times negative 1 over s minus 5. That equals 1 over s minus 5. So that is the Laplace transform for the exponential function e to the 5t. All right, we need to be careful here with the result for the Laplace transform, because we need to specify a condition here. So this is good for s greater than 5. Why is that? Because if this is less than 5, on the other hand, okay, go back to the original integral. All right, what happens if s equals a negative number, negative 5? So that negative number times the negative in the exponent of the exponential will become positive. So what's the problem with that? The problem here is that we will have an increasing exponential function multiplied with another increasing exponential function, and as a result we are going to end up with a divergent improper integral. So that's why we need to be very, very careful with these conditions. All right, well, later we won't be really setting these conditions. I'm setting it now just to stick with the definition of the Laplace transform and how that in terms of the integral, how that integral could potentially converge or diverge. All right, well, so that being said, well, we can find the Laplace transform, say, of e to the 3t. That would be 1 over s minus 3. The Laplace transform of e to the simply t, e to the t, 1 over s minus 1. The Laplace transform of e to the negative 4t. That would be 1 over s minus negative 4, which would be 1 over s plus 4. Later, again, we will use some formulas to find the Laplace transform of other functions. All right, let's do one more using the definition of the Laplace transform, using the integral. All right, so the Laplace transform of sine of some number times t, well, so this will be the integral, change color, okay, so this will be the integral from 0 to infinity of the function to be transformed. Well, let me actually write e to the negative st times the function to be transformed, sine kt dt. All right, this integral would be madness to evaluate it using integration by parts. So that's one of those integrals that you need um, to treat it like an equation, because you will have to do two iterations of the integration by parts process. And well, after the second iteration, the original integral shows up and then it becomes a mess. All right, if we were to evaluate this integral by integration by parts, it would have taken at least a page, if not a page and a half. However, instead, we're going to use an integration formula from the calculus textbook in order to evaluate this quicker. Okay, that formula is right here at the top. It's the integral of e to the bx sine of ax dx, that is 1 over a squared plus b squared times e to the bx times b sine ax minus a cosine ax. All right, well, so in this case, so b, so using this integral formula, so b equals to negative s, okay, sticking to the integral form, and a equals to k. All right, so what is this? Okay, using the form, this is 1 over a squared, which is k. All right, this is k. So that is k squared plus negative s squared e to the bx, which is negative s t, times b, which is negative s, times sine kt minus k, which is a cosine kt. Okay, and I'm going to evaluate this between 0 and infinity. Okay, guys, I know technically we should be very strict with the limit notation for what's it called, for the improper integral, but I'm going to skip some of the details just to make the process a bit shorter and quicker. Okay, so this will give us the following. Number one, so this is equal to 1 over s squared plus k squared times, on the one hand, okay, e to the negative st times negative s sine kt minus a cosine kt, or rather k cosine kt. And I'm going to evaluate this for t approaching infinity. Minus, well, actually, yes, minus e to the negative st, okay, same, essentially. I'll show you what I'm going to do here. Negative s sine kt minus k cosine kt. And I'm going to evaluate this at t, the lower limit at 0, and I'm going to close the bracket. Okay, let's simplify all these calculations. Let's perform this calculation. So number one, for t equals to 0, this quantity cosine k times 0 equals to 1. All these terms, because sine of 0 equals to 0, this is going to go to 0. And then e to the negative s times 0, this will be equal to 1. Right? Over here, number one. Okay, what is cosine at infinity? Okay, so cosine at infinity, that's actually an oscillation between plus and minus 1. What about sine at infinity? That's an oscillation as well between plus and minus 1. And lastly, where is e to the negative st at t equals infinity? Okay, so that goes to 0. Okay, so it doesn't matter what the value of the sine and the cosine function is for large values of t. If it's oscillating between 1 and 1, whatever that is, multiply that by 0. All this quantity right here equals to 0. Okay, so this is going to leave us with the following. Okay, so that equals 1 over s squared plus k squared times, okay, so this big 0 minus 1 times 0 minus 1. Okay, not minus 1, minus k, right? That's the term that survives because it's cosine of 0, which is 1. 1 times k, that's k. Okay, and okay, so this equals, okay, so 0 minus k is negative k. Negative k times negative 1, positive k. Positive k plus 0, it's still positive k. And positive k, so this equals to, all this, okay, let me just, this is equal to k. And this k multiplying with this rational expression equals k over s squared plus k squared. And that is the Laplace transform of sine of kt, where k can be a 5, can be a 7, whatever that number is. There's no, that's no big deal. All right. Well, so I mean, of course, we don't want to evaluate the Laplace transform of more complex or more elaborate functions using the integral definition. So for this, we have the transform of some basic functions. So the Laplace transform of t to the n, that is n squared, n factorial over s to the n plus 1, or instead of n factorial, you might want to use gamma of n plus 1. And we're going to use the gamma function version when we find the Laplace transform of t to the 1/2, that is the Laplace transform of the square root of t. So that's why we had to go through the process of the gamma function, because again, as I mentioned back then, it's a very, very powerful tool to evaluate other Laplace transforms and evaluate other integrals. Actually, these same integrals we use to evaluate Laplace transform that otherwise would have been so very time consuming. All right, you guys have no idea of how much time have we saved by using the gamma function approach instead. Okay, that being said, well, so how about we use these formulas right here to find the Laplace transform of other functions. But before looking at those exercises, let's talk about the linearity of the Laplace transform. Okay, so if we're given some functions f of t and g of t to be transformed and some constants alpha and beta, well, oftentimes we will find the Laplace transform of multiple functions, like example 2a, example 2b right here. Those are combinations of these functions and potentially multiplied by some coefficients. All right, well, so that means we can multiply alpha times the Laplace transform of f of t, which will be alpha f of s, plus beta times the Laplace transform of g of t, which is beta big G of s. All right, well, so, okay, let's apply these Laplace transform formulas to find the Laplace transform of the following function. So, here, let's use the linearity property to write here. So, 4 times the Laplace transform of e to the 2t plus 3 times the Laplace transform of t to the 4th power minus 8 times the Laplace transform of 1. Okay, so this will be using the formula, the Laplace transform of e to the at, that is 1 over s minus a. So if you're given 2, change the sign to the opposite sign, and this will be equal to 4 times the Laplace transform of e to the 2t, which is 1 over s minus 2, plus 3 times the Laplace transform of t to the 4th power, that is, in this case, 3 times 4 factorial over t to the 4 plus 1, minus 8 times the Laplace transform of 1, which is 1 over s. Okay, so let's just simplify and multiply. So here, 4 times 1 equals to 4 over s minus 2 plus 3 times 4 factorial. But first of all, 4 factorial, that's 24. 24 times 3 equals to 72 divided by t to the 5th power minus 8 times 1, which is 8 over s. Final answer, right? So that is our final answer to finding the Laplace transform of the function of this combination of functions. All right, well, now let's find the Laplace transform of the function 2 cosine 5t plus 7 sinh 3t. That's a hyperbolic function. Number one, might want to use the linearity property, that is 2 times the Laplace transform of cosine 5t plus 7 times the Laplace transform of sinh 3t. Okay, all right, well, let's use the formulas to find the Laplace transform of the cosine function and the Laplace transform of the hyperbolic sine function. They're at the top of the almost at the top of the page. So the Laplace transform of the cosine function, that is s divided by s squared plus k squared, that is the number that multiplies t, quantity squared. And the Laplace transform for the hyperbolic sine function, it's k over s squared minus k squared, where k again is the number that multiplies the variable in the argument of the functions, just so you can see the resemblance of some of the functions, well, of some of the Laplace transforms of some of the functions rather. So see how the Laplace transform of sine is very similar to its hyperbolic counterpart. However, they just differ by the sign in the denominator. While the original trigonometric function has a plus in the plus sign, the hyperbolic counterpart has a negative sign. Same thing between the Laplace transform of the cosine function and the Laplace transform of the hyperbolic cosine function and hyperbolic cosine function. And again, plus, minus. All right. So let's use those formulas to find the Laplace transform. So this will be 2 times the Laplace transform of cosine, which is s, divided by s squared times, plus 5 squared plus 7 times the Laplace transform or hyperbolic sine function, that is k, which is 3 over s squared plus k, which is 3 quantity squared. All right, well, this will be equal to 2s divided by s squared plus 25 plus 7 times 3, which is 21, divided by s squared minus 9. All right, and that is the Laplace transform of this combination of functions. All right, so let's evaluate one more Laplace transform. Well, so what about the Laplace transform of the square root of t? Okay, well, number one, you might want to write the square root of t as t to the 1/2. So here is the thing. If you were to use the Laplace transform of t to the n, this would have been 1/2 factorial divided by s to the 1/2 plus 1. All right. However, as we discussed in our notes on the gamma function, we don't find the factorial of a rational number. Instead, we evaluate the gamma function of that rational number. Well, at least we know techniques, and we have discussed in gory detail for Laplace transforms of odd multiples of a half. Okay, well, so because think about it, go back to the notes right here, or go back to the formulas. That's why I added an extra line right here to relate the n factorial with gamma of n plus 1. All right, so what are we going to do? So number one, we will write this 1/2 factorial as gamma of 1/2 plus 1 divided by 1/2 plus 1, which is s to the 1/2 plus 1, s to the 3/2. Okay, how do we evaluate gamma of 1/2 plus 1? Recall that gamma of n plus 1 equals n gamma of n from our notes on the gamma function. So this will be 1/2 gamma of 1/2 divided by s to the 3/2. Okay, but what's gamma of a half? Didn't we go through a big derivation of what gamma of a half is? Yes, we did. So gamma of a half is square root of pi. So that equals 1/2 square root of pi divided by s to the 3/2. Okay, well, although this is the final answer, you may not like having this complex fraction. So let's work through this result and make it look a little nicer. Well, number one, this 1/2 is the same as 2 in the denominator. That equals the square root of pi divided by 2 s to the 3/2. However, you guys agree, hopefully this is s to the first power times s to the 1/2. I mean, comes from the very first step. So this will be square root of pi divided by 2s square root of s. And using properties of radicals, we can rewrite this as 1 over 2s square root of pi over s. That'll be our final answer. That is the Laplace transform of square root of t. Alright, so, well, what else besides the Laplace transform? Well, so we're going to discuss a little bit, just briefly, about existence of the Laplace transform, because not all functions have a Laplace transform. So, the question here, the idea here is that the integral that defines the Laplace transform does not always converge, because some functions actually end up being functions whose improper integral actually diverge. So how are we going to know when the Laplace transform exists? Well, so there are two conditions for the Laplace transform to exist. Number one, the function f of t is piecewise continuous in the interval 0 to infinity. And we're going to talk about this piecewise continuous later in the chapter when we talk about Heaviside functions and unit step functions, you'll see. All right, number two, f is of exponential order. What does that mean? It means that the absolute value of the function is less than or equals some number e to the some number times t for all t greater than t with an uppercase t. In other words, so a function that grows faster than any positive linear power, as we can see it's a linear power of e, is not an exponential, is not of exponential order. Examples right here. Okay, so compare the graph of e to the t, which is the exponential function, and compare it to the graph of t, which is just a diagonal line. So in this case, the exponential function grows faster than the linear function. If it were the other way around, if that function grew faster than the exponential e to the t, then it wouldn't be of exponential order. What about e to the negative t? As we can see, well, even e to the negative t, it's a decreasing function. So actually, e to the t, it's still dominating, it's still growing faster than the other function. Actually, the other function, it's decreasing, not increasing, not growing. All right, so e to the t is a function of exponential order. The function 2 cosine of t, well, actually this is an oscillating function. Well, goes down, goes up, or rather decreases, increases, decreases, increases, but actually it doesn't increase faster than 2e to the t, all right? However, the function e to the t squared does not have a Laplace transform, and that's because this function grows faster than any linear exponent or any linear power of e. Okay, linear power of e, this is ct. And that actually, this is t squared. A t squared exponent or a quadratic exponent will make the exponential grow faster than a linear exponent. Therefore, e to the t squared will not be of exponential order. All right, but again, we're going to talk about this Laplace transforms for especially for the piecewise continuous more in depth later. So this is the end of the notes for the introduction to the Laplace transform, which in this case we just took the Laplace transform of some of the functions using the formulas and using the definition, right? So this is the end for these notes.